Hello there, this is Professor Shannon Gracie. We are working on section 1.2 from the Precalculus Enhanced with Graphing Utilities by Sullivan and Sullivan, and we'll be covering intercept, symmetry, and graphing key equations today. So let's get started with a warm-up right here. This is just kind of a solve for x type of thing, and then the second warm-up, again solve for x, but it is quadratic in form. So why don't you guys pause the movie and warm it up. Okay, let's see how you did. So we have this 4 that needs to be distributed. So we have the 4 times 2x is 8x, and we'll have plus 32. That is equal to 3 minus 5x. We've got like terms here, so we'll get negative 5x plus 32 is 3 minus 5x. If I subtract the 32 from both sides, I will have negative 5x is equal to negative 29 minus 5x, and adding this 5x to both sides, oh, something a little creepy's going on here. Notice you're going to get, this will zero out, so you actually get 0x, which is 0, and supposedly this is equal to negative 29, and that, of course, is false. So the way you represent the solution set is you simply write empty set brackets, or you can do it with this notation here, the null set. But you never put the null set inside the empty set brackets. You do one or the other. How'd you do? Awesome. All right, let's move on. The next one, quadratic in form. So you learned several ways to solve an equation like this. I'll go ahead and solve by factoring. So if it is indeed factorable, so we'll get 2x squared minus x minus 3 is 0. So if you recall, you put the overall product a times c, so that'd be 2 times negative 3 goes at the top of the x. And then at the bottom of the x, you put this last term here. And we're looking for two numbers that multiply to be negative 6 and combine to be negative 3. So we'll have opposing signs. And I believe that the two numbers will be negative 3 and positive 2. So, factoring by grouping, we'll have 2x squared minus 3x plus 2x minus 3 is 0. So doing this first group here, so you can do it like a red group and a blue group. So we can factor out an x from the red group, and we're left with 2x minus 3. And then we already have that 2x minus 3, so let's put a plus 1 as a placeholder. Oops, and then we'll have the 2x minus 3 is 0. So this is how the red group factored. This is how the blue group factored. Now we have a common binomial factor of 2x minus 3. So we'll actually factor that out, and we'll be left with x plus 1, and that'll be equal to 0. So using the zero product property, we'll have 2x minus 3 is 0, or x plus 1 is 0. 2x will be 3, so that would give us x is 3 halves, or x is negative 1. And we got two distinct solutions that satisfy the equation, so we will write them like this. Okay, do we feel all warmed up? Good, good. So next up, procedure for finding intercepts. So to find the x-intercept or intercepts if there's more than one of the graph of an equation, what you do is you let y equal to 0 in the equation and you solve for x, where x is a real number. And to find the y-intercept, if you have one, and again, you could have more than one if you're not dealing with functions, you let x equal to 0 and you solve for y, where y is a real number. So we're not going to be using any of the complex solutions that have I in them. Recall the square root of -1 is I. We're not interested in complex zeros, just real zeros. Okay, so here we go. Find the intercepts and then graph each equation by plotting points. So here we are. The x-intercept, if any, will be 0. So I'll go ahead and show what I'm plugging in 0 for. So we would let y equal 0. And when we solve for x, do you see we get 6 is x? So the ordered pair, 6, 0, is the intercept. In the Pearson MyLab, the MyMathLab, they will often just have you do the coordinates. So instead of entering the ordered pair, you'd just be entering 6 into the computer program. I like to see the ordered pairs on the written exams. Okay, so the y-intercept, we now, instead of letting y as 0, we let x be 0. So we get y is -6. So the ordered pair, 0, -6, is the y-intercept. So now, doing our graph, we already have 2 ordered pairs, right? We have the intercepts. And why don't we go ahead, we'll start out by graphing, a few extra order pairs than what we might need. Just as a reminder, we already did this one where x is 0. We got y was 0 minus 6, so we got y was -6. So we'll use that as one of our ordered pairs. And why don't we go ahead and try, you tell me. How about -2 and maybe +3, something like that? So if y is, or if x rather, is -2, we would get a result of y is -8. Good. So we'll have the ordered pair, -2, -8. Plugging in 3 for x, we would get 3 minus 6. So we would end up getting y is equal to -3. So we would get the ordered pair, 3, -3. So let's go ahead and have our scale go from plus or minus 10 on each axis. So each of these tick marks has a distance of 1. And this is our x-axis and our y-axis. And recall we had the x-intercept was 6, 0. So 1, 2, 3, 4, 5, 6, 0. And then we'll plot these ordered pairs. So 0, 1, 2, 3, 4, 5, 6. And then -2, -8 is here. So it looks like this is turning out to be a line. And you would have learned that you had the format of a line from your intermediate algebra stuff or beginning algebra stuff. All right. Doing okay so far? All right. So next up, let's see what we have. So this one, same stuff. We have a, it's going to be a curve this time. We've got that x squared going on. So let's find our intercepts, if any. So the x-intercept, again, we are going to let y equal 0 in the equation. So this gives us 4x squared is 4. If we divide both sides by 4, then we end up with x squared is equal to 1. Now, again, another skill from intermediate algebra, we square root both sides. We get a result of x is equal to plus or minus 1 by the square root property. So our intercepts for the x-intercepts will be at -1, 0, and 1, 0. All right. So the y-intercept, we have one. We let x equal 0. And then we'll be isolating y. So this all zeroes out. So y will equal to 4. So our intercept will be at 0, 4 for the y-intercept. So let's get a few more ordered pairs and take a look at what we've got going on. So I think that regular scale is going to work out okay again. So the standard scale, plus or minus 10 on the axes, or the standard viewing window. And let's plot the ordered pairs we already have. So we have -1, 0, 1, 0, and 0, 4. So -1, 0, 1, 0, and then 0, 1, 2, 3, 4. So let's get some more values for x, or set values for x and solve for y. So if x is equal to 2, we'll have 4 times 2 squared plus y is 4. That's going to give us 2 squared is 4. 4 times 4 is 16 plus y is 4. And then we'll get a result of y is -12. So this is an important lesson. Notice I set the scale based on those other ordered pairs, and look, I've already gone beyond my scale for the y-axis. So let's go ahead and modify this. We'll only need to change one ordered pair. I'm going to go ahead and have this axis go from plus or minus, go from -20 to +20. So this will be 20, this will be -20. So each tick mark on the y-axis will have a distance of 2. So my intercept will now be at right here, 0, 4 will land right there. Okay, so we've got that ordered pair at 2, and then -12, 2, 4, 6, 8, 10, 12. And do you guys remember your work with parabolas? We've got symmetry going on. So I'll go ahead and work out the algebra on this, but I'm going to tell you right away, we're going to get a y value of -12 when we plug in -2 for x, because this graph is symmetric with respect to the y-axis. Okay? So let's check it out and see if I'm right. So do you see that -2, the quantity squared is +4, and 4 times 4 is 16. And then we'll get that same result of -12. So there we go. And then I think 3 is going to take us way far away from from the axis there. So 5 ordered pairs is enough to do this graph. General rule of thumb is when you have a curve, as long as you have 5 ordered pairs that give you an idea of the shape of the curve, you'll be good. Let's see. Okay. So, speaking of symmetry, here's some official definitions for symmetry. So a graph is said to be symmetric with respect to the x-axis if for every point x, y on the graph, the point x negative y is also on the graph. And we have examples of these coming up. A graph is said to be symmetric with respect to the y-axis if for every point x, y on the graph, the point negative x comma y is also on the graph. So let's scroll back up to this guy. Do you see that the ordered pair 1, 0 is on the graph? And so the ordered pair negative 1, 0 is also on the graph, right? So you have this fold line right at the y-axis. So you could literally fold this graph in half right there, and the graph would land on top of itself. Kind of like, you know, when you're making, when you were a kid in Valentine's Day, how did you make the little hearts, right? You folded the paper, you cut out half the heart, and you had a symmetric heart. Mine always came out kind of dorky, but it was symmetric. All right, so a graph is said to be symmetric with respect to the origin if for every point x, y on the graph, the point negative x, negative y is also on the graph. So let's just draw a picture of some situations. So I'll draw a picture and you try to guess which situation I gave you a picture of, and then we'll write it at the top there. Okay, so let's see. Let me do okay, so you guys tell me, so the definition for symmetry, you know, if I replace, which one do you think I have reflectional symmetry? So if I fold this graph on something, what will it, on one of the axes, will it have symmetry? Or you can go straight to the definition, right? So here, this is the ordered pair 5, 5, right? And this is the ordered pair 5, negative 5. So if you think of this as, if you think of the 5, 5 ordered pair as your kind of x, y, this 5, negative 5, do you see that the x is the same, but the 5 is just the negative of the other, the opposite of this one. So it looks to me like this guy is symmetric with respect to the x-axis. Good so far? Okay, so now let's see. Let's do another one. So let's see what we have. Do a point here. Okay, what do you think about this guy? So let me label some of these points. This is 1, 1, 0, 0, and this is negative 1, negative 1. So the 0, 0 won't help us too much, but if you look at the fact that the 1, 1 is on the graph, and then the opposite of 1, comma, the opposite of 1 is on the graph. So this guy seems to be symmetric with respect to the origin. Okay, and then finally, this one won't be too hard to guess, right? But let's draw sort of a funky one. Let's say we had something like this. So this is 1, 2, 3. This is 3, 3. And then let's say we had this point. Oops. This is negative 3, 3. So what would you say about this one? Good. It's symmetric with respect to the y-axis. Okay. So here's some official tests for symmetry, and this can really aid in graphing. So we'll check it out. So if you want to test for symmetry on the x-axis, you replace y by a negative y. If an equivalent equation results, so you get the same thing back, the graph of the equation is symmetric with respect to the x-axis. So for the y-axis, you replace, x by negative x. We don't need parentheses right here. In the equation, if an equivalent equation results, the graph of the equation is symmetric with respect to the y-axis. Okay, test to see if we have symmetry with respect to the origin. So this time you replace x by negative x and y by negative y. If an equivalent equation results, the graph of the equation is symmetric with respect to the origin. So here's some examples. So we're going to plot the point 4, negative 2. I would plot that point just in black. I'll just do the standard viewing window. And if we plot 4, negative 2, it'll be 4 to the right and then 2 down. Okay. So this is 4, negative 2. Now, if I name this point A, we're supposed to plot the point that is symmetric to 4, negative 2 with respect to the x-axis. So we're supposed to replace y with the opposite of y. So, do you see, this would yield the point A, which is equal to 4, comma, the opposite of negative 2, which of course the point A would be 4, 2. So we would be up here. So that's point A. The y-axis, point B, would be, now we replace x with negative x. So negative 4, comma, and we keep that negative 2. So symmetry with respect to the y-axis would be at 1, 2, 3, 4, 1, 2 down. So that's point B. Now, symmetry with respect to the origin. You replace x with negative x and y with negative y. So point C will be negative 4 and the opposite of negative 2. So point C will be negative 4, positive 2. So that's going to be over here, and that one is symmetric with respect to the origin. Okay? Okay, so now that was just dealing with, the 3 situations with a single ordered pair. So now let's do separate graphs, and we're going to draw the complete graph so it has the type of symmetry indicated. So why don't you guys try to do this one on your own. Go ahead and pause the movie and check it out. Okay, let's see how you did. I'm looking at this graph and I see that 1 is on the graph. So if I want symmetry with respect to the x-axis, I replace y with negative y. So that would take me to 1, negative 1. It also looks like the ordered pair 2, 4 is on the graph. So if I replace 4 with negative 4, I'd be at 2, 1, 2, 3, negative 4. So it's going to go something like that. All right. Now, the y-axis. Again, we're looking at those ordered pairs we were talking about, but now you replace x with negative x and you leave the y alone. So here, that would take us to negative 1, 1, and then negative 2, 4. So we'd be something like this. Alright, so the origin. Now, we replace both the x and y's by the opposites. So 1, 1 will be at negative 1, negative 1. 2, 4 will be at negative 2, negative 4. So it'll go something like that. How'd you do? You do all right? It's fun drawing pictures, huh? Okay, so now this next example, there's like 4 parts. So on this one, at any time, go ahead and pause the movie and try them on your own. We're going to, actually this one might only have a couple. Yeah, and then, or no, there's 4 of them. So what we're going to do is we're going to list the intercepts and then test for symmetry. So sometimes, sometimes you start getting used to these and you know which test you should run first, but I'm just going to go in the order, x-axis, y-axis, origin, just to be thorough. So let's start with the intercepts. So x-intercept on this guy, remember we set y equal to 0, and so y is being squared, equals x plus 9. So the x-intercept is going to be at negative 9, 0. And remember, on the program, they'll just ask you for the coordinate. So you'd say x is negative 9. And the y-intercept, we set x equal to 0. So we've got y squared is equal to 0 plus 9. Y squared equals 9. Utilizing that square root property, we will get y equals plus or minus 3. So you get two y-intercepts, 0, negative 3, and at 0, 3. So, testing for symmetry. The x-axis. Remember, with the x-axis, you replace y with negative y. And see if you get the same thing. So, I'll do them in a different color. So, negative y squared equals x plus 9. Well, the negative goes away in the square since it's in the parentheses, equals x plus 9. And do you see that works? That's the original. So what did we find out? The graph is symmetric with respect to the x-axis. Okay, so we got all the things they asked for. They're all boxed. Okay, part B. So, our intercepts. Oh, actually we're doing them like this. X-intercept. So 0 is equal to x to the 4th minus 2x squared minus 8. This one is quadratic in form. You can write it like this. In intermediate algebra, you were taught to actually do a u substitution. I think if you just see that it's factorable, you need an x squared and an x squared. You need to have a product of negative 8, and you need to have them combined, the middle terms combined to be negative 2. So I believe minus 4 and plus 2 fits the bill. If you need any review on factoring or solving equations like this, I believe this is like section 11.4. I did it in out of the Blitzer textbook. It's in my intermediate algebra videos, or you can go to www.mathchick.net and go to the intermediate algebra site if you want to watch the video. So here we go. We have 0 is x squared minus 4, or 0 is x squared plus 2. 4 equals x squared. If I square root both sides, I will get plus or minus 2 equals x. Now over here, look what happens. Negative 2 is x squared. Do you see this is going to be imaginary? I only want my real results so that I have my intercepts. The imaginary doesn't help us. It means it's going to be floating, in this case, above the axis. So my x-intercepts are going to be at negative 2, 0, and 2, 0. Okay, y-intercept. Y equals, we're setting x equal to 0. There we are. And we'll have y equals -8. That was a lot easier, wasn't it? So this intercept will be at 0, -8. And symmetry. So, x-axis. We replace y with -y and see if we get the same equation. So, -y equals x to the 4th minus 2x squared minus 8. -y is x to the 4th minus 2x squared minus 8. Nope, not the same. Y-axis, replace x with -x. See if you get the same thing. So we would have y equals -x to the 4th power minus 2 times -x squared minus 8. So this would give us, we're raising these to even powers, so the negative will go away. And it looks to me like we get the same thing, so that one checks out. So this one will be symmetric. We should probably, yeah, I should say the graph is. The graph is symmetric. With respect to the y-axis. Okay, moving right along. We've got y is equal to the 5th root of x. So intercepts. The x-intercept is at y equal to 0. So just a little review. We want to match the index, raise it to the same power as you see in that index, but you're still going to get 0 over here. So the x-intercept is 0, 0. You're going to find out that's going to be our y-intercept too, but we'll go through the process. So now we'd be evaluating the 5th root of 0, which is 0. So our y-intercept is 0, 0, right at the origin. Symmetry. Okay, x-axis, remember, we replace y with -y. See if we get the same thing. So -y equals the 5th root of x. We get this result, which is not the same. Now we have our y-axis. We replace, getting a little crazy here, x with -x and see if we get the same thing. So that will give us y equals the 5th root of -x, which is, you've got a -1 to the 5th times x, so you can pull out a negative and you get the 5th root of x, and that is not the same. So let's go up here on the side here and do the origin over here. So this one you replace x with -x and y with negative y, and see if you get the same thing. So negative y equals the fifth root of negative x. We would get negative y equals negative fifth root of x if you multiply both sides by negative 1 or divide both sides by negative 1. Both negatives will go away, and you get y is the fifth root of x. So that one checks out. So the graph is symmetric. Graph is symmetric with respect to the origin. All right, moving right along, my friends. Part D. So, you got to be careful with this guy because do you see you have an excluded value here? X cannot equal to zero. It's actually a vertical asymptote for the graph. We'll be learning more about those as we go on. So here, do you see there will be no y-intercept? Because if I plug in x equals 0, I will zero out the denominator. So we'll start with the y-intercept. We'll say none, since x equals 0 is not part of the domain of this equation relation. It's actually a function, I think you'll find out. So none. And the x-intercept, let's check it out. If I set y equal to 0, do you see that if the numerator is 0, the whole fraction will be 0? So I'm just going to say 0 is equal to x to the fourth plus 1. Negative 1 is equal to x to the fourth, but this again will be imaginary. And we're dealing with the real numbers, so we would say none. Okay, so now let's test for symmetry. The x-axis, remember, we replace x with, oops, my bad, y with negative y, and see if we get the same thing. And we will not. Y-axis, we replace x with negative x and see if we get the same thing. So y would be negative x to the fourth plus 1 over 2 times negative x to the fifth. So this would give us positive x to the fourth plus 1 over negative 2x to the fifth, which is not the same. So now let's test the origin. So remember, with the origin, you replace x with negative x and y with negative y, and see if you get the same thing. So we would have negative y equals negative x to the fourth plus 1 over 2 times negative x to the fifth. Negative y equals positive x to the fourth plus 1 over negative 2x to the fifth. If I multiply both sides of the equation by negative 1, then I will get y is equal to x to the fourth plus 1 over 2x to the fifth. So that one checks out. So the graph is symmetric with respect to the origin. Okay, so let's see, let's kind of put this stuff together and let's see what it tells us. This probably might not have seemed really, really interesting to you, but if you apply it, to graphing, I think you'll see the use for it. So first we have sort of one of those deep thinker problems. So if you have a comma negative 5, on the graph of y equals x squared plus 6x, what is a? Well, for me, the easiest thing to do would be to, plug these values in. I've been given a y value of negative 5, and I've been given an x value of a. We just don't know what it is. So let's see what shakes out when we substitute these values in. So we'll get negative 5 is equal to a squared plus 6 times a. So this is the y value that we substituted in, and this is the x value. So, this kind of looks quadratic in form to me. So let's get 0 on one side and see what happens. I'm adding 5 to both sides, and this guy will factor. We'll get 0 is a plus 1 times a plus 5. So we would get a plus 1 is 0, or a plus 5 is 0. So a will be negative 1, or a will be negative 5. And we're good. And you can plug it into the original equation and see, and you'll see that you get a true result. Okay. So moving right along. How to graph key equations. So we're going to graph these equations, and we're going to use intercepts and symmetry. So here we go. Check out this graph. Y equals 1 over x, or this equation rather. So do you see that if I put in 0 for x, I would end up with something that is undefined? So again, this turns out to have a vertical asymptote at the y-axis. The line x is 0. So we are unable to plug in 0 for x, which means there is no y-intercept. Now, if you set y equal to 0, you're basically saying that 1 is 0. So there's no x-intercept. So, no intercepts. So now let's check our symmetry. I'm not going to write all the words, okay? We're just going to plug in the values. If you need to refer back to the words, you can. So for the x-axis, you replace y with negative y, and you see if you get the same thing. So negative y equals 1 over x. We would have negative y is 1 over x. That is not the same. The y-axis, you plug in negative x for x and see if you get the same thing out. And that is not the same. And the origin, you replace negative x with x, or x for negative x, and you replace y with negative y and see if you get the same thing. So we'd have negative y equals 1 over negative x, negative y equals negative 1 over x, and multiplying both sides by negative 1, we would get y equals 1 over x. So that checks out. So this is going to be symmetric with respect to the origin, and it has no intercepts. So what this is going to help us with, this symmetry business, will help us finding ordered pairs. So I'm not going to make the scale this time until I find, some ordered pairs. So let's check it out. Let's just do some positive values, and then we'll get some other ordered pairs using symmetry. So let's do like maybe, 1/2, 1 and 2. How about that? So y equals 1 over 1/2. That would give us y equals 2, because you would invert and multiply that 1/2. So it would be 1 times 2 over 1. So our ordered pair would be at 1/2, comma 2. And then the next one, when I plug in 1, we just get y is equal to 1. And then when I plug in 2, we'll get y is equal to 1/2. So the way symmetry will help us is it's telling us, the symmetry about the origin is telling us that if 1/2, 2 is on the graph, then negative 1/2, comma negative 2 is also a point on the graph. So we can do the same thing with the other two to get the other side of the graph. So let's do our scale. Do you see that we have some half units going on? So why don't we just do a scale? We'll kind of zoom in, if you will. And if we just go where each of these tick marks is a half unit, I think that will give us a good picture. So we have 1/2 and then 1, 2. So what we're saying is that by symmetry, negative 1/2, negative 2 is also on the graph. Are we good? Awesome. All right, so 1, 1 is on the graph. So negative 1, negative 1 is on the graph. And then 2, 1/2 is on the graph. So negative 2, negative 1/2 is on the graph. And remember, we had said there was going to be a vertical asymptote here. So our picture is going to look something like this. And you see that that's reflectional symmetry about the origin. Pretty groovy. Okay, and that is, again, a basic graph that you want to know. We'll be talking more about the library of functions when we get to functions, and that's a good one to know. Okay, part B. We have x is equal to y squared. So let's think about those intercepts. So the x-intercept, let y equal to 0. So we'll just get x is equal to 0. So our intercept will be at 0, 0. The y-intercept, you probably are guessing it's going to be at the origin, but I'll go ahead and do the work so you have the process. You let x equal to 0 and solve for y. So you can square root both sides, and you'd end up getting plus or minus 0 is y, but 0 is neither positive nor negative, so this is what we would get for the intercept. Okay, so now we've got a couple ordered pairs. Let's check out the symmetry. So the x-axis, remember we're replacing y with negative y to see if we get the same result. So x is equal to negative y, the quantity squared. X equals y squared. Bingo, we got it this time. We're going to have symmetry with respect to the x-axis this time. So that will help us with ordered pairs. We've already got one ordered pair of 0, 0. Let's get a few more. So we've got, let's let y equal certain values. I know I made it kind of small right here. Sorry, this column. If we let y equal like negative, we'll do positives, and then we'll get the negatives the other way. So positive 3, positive 2, and 1. Then x will be 3 squared, which will be, good, 9. So we'll have the ordered pair 9, comma 3. This guy, x would be 2 squared, which is 4. So we'll get the ordered pair 4, comma 2. And this one, x would be 1 squared, which is 1. So 1, comma 1. And we are going to use symmetry to get 3 additional points. So let's use our regular viewing window. I'll do that in black. There we go. And we will go ahead and graph the 0, 0, the intercepts. And then we have an ordered pair at 9, 1, 2, 3. So that means that using symmetry, we replace the y value 3 with the opposite of 3, which is negative 3. So we'll have another ordered pair at 9, and then 1, 2, negative 3. 4, 2, 1, 2, 3, 4, 2. So where's my other ordered pair going to be? Good, at 4, negative 2. You see that symmetry on the x-axis? And then 1, 1 will yield 1, negative 1. And so we've got a nice graph of a conic section here. Good so far? All right. So this one here, y equals x cubed. So we'll get our intercepts. The x-intercept will be setting y equal to 0 and solving. We have a cube, so if we cube root both sides, we will get 0 equals x. So the x-intercept will be 0, 0. Y-intercept, you're probably already guessing. If we let x equal 0, you're going to have 0 cubed. So we'll get y equals 0. So again, the x-intercept is the same as the y-intercept, 0, 0. So symmetry, let's check it out. So x-axis, place y with negative y, see if we get the same thing, and we do not. Whoops, we do not. the y-axis, we replace x with negative x and see if we get the same thing. And we do not. And the origin, we replace each of them with their opposites. So we'll have negative y equals negative x cubed, negative y equals negative x cubed. And then multiplying both by negative 1, we'll have y equals x cubed, which is what we started with. So that is what we have. We have symmetry with respect to the origin. Okay? So, let's see what we have going on. Let's do a couple ordered pairs. I don't know, we could do, how about 1/2, because we already have 0, 0. So 1/2, 1, and 2. We'll do that. So y would equal to 1/2 cubed would give us a result of y equals 2 1/8. So 1/2, 1/8. Y equal to 1 cubed gives us y equals 1. So 1, 1 is on the graph. And y equals 2 cubed gives us y equals 8, so the ordered pair 2, 8 is on the graph. So symmetry with respect to the origin says that, hey, if you have point xy on the graph, negative x comma negative y will be on the graph as well. So we'll flip the signs on each coordinate after we plot the initial point, and we'll get an extra point using symmetry. So I'm thinking that on the x-axis, why don't we do a scale of 1/2, and on the y-axis we'll do our regular scale. So the total will be 5 on the x-axis. So then we have this ordered pair, 1/2, and then 1/8 is going to be real close down here. And then since we have symmetry with respect to the origin, the ordered pair, -1/2, -1/8 is going to be on there. We also had 0, 0 from the intercepts. And what else? We've got 1, 1. So we will have -1, -1. And then we had 1, 2, 8. So we'll have -1, -2, and then -8s on the graph. And that's our picture using symmetry. So you're learning more tools now. You're going to learn even more tools when you're in calculus for curve sketching. But this is a preview for you. And that wraps it up for this evening for me. And I hope you are doing well. Make sure that you work some problems from the problem set to get this set in your brain. Have a fabulous evening. Bye.